Hi, Honors Pre-Calc. Sorry for the delay in this video, but here I am. And because part of class yesterday was supposed to include your Desmos exploration, this lesson will not be that long. A lot of this that you're supposed to be learning is through exploration, so please don't forget to turn in that homework. I think I extended the deadline on that. And not only do you have to have a reasonable and thoughtful comment on most of the slides, remember to submit your page, I believe it's 23 from Desmos. So today's lesson, which was supposed to be yesterday's lesson, is on graphs of polar equations. And remember that these polar equations are closed curves. Closed curves, like circles, are not functions. And this is going to come into play as we look at some of our polar equations using r and theta, and also when we're starting to describe some of the characteristics of our polar curves. So we will study today symmetry. In analyzing our polar curves, we will talk about symmetry. We will talk about petal length. We will talk about number of petals. We will talk a little bit about domain, specifically today restricting domain. And then these last bullets are really just names of types of polar graphs that some of which we'll see today and some of which you should have seen in your Desmos exploration. Other polar graphs are circles, which you've already looked at, or we've already looked at a little bit, and also something called cardioids. Don't forget that second I. Cardioids are really a type of limaçon. This is said limaçon. Comes from the French word that means snail for some reason. So limaçon is French for snail, and cardioids is a type of limaçon. So our polar curves are nothing more than a special case of parametric curves. There is a motion for horizontal movement. There's an equation for horizontal motion. There is an equation for vertical motion. All of these graphs have some kind of circular or cylindrical symmetry, even though they have simple equations. Remember, the first day we did polar, we talked about how one of the reasons we have polar equations is it's making very complicated rectangular equations, like circles that have centers that are not at the origin. It makes them simple. So our polar equations are much simpler than our rectangular equations, and you will find that, especially if you take calculus next year, very useful. Okay, so for these graphs, we are going to be talking solely in terms of r and theta. And today's lesson will talk about using our polar equations to see the graphs using GeoGebra, as well as I'll show you how to do it also in your calculator to help answer some of these questions about our analyzing of the polar curves. Specifically today, I'll show you how to use your calculator to find out how to restrict the domain for, say, a petal on one of our roses. There's really nothing else on this page except to say, make sure that you can do this. I'm going to go back and check the quiz. Ms. Patel clued me in on the fact that students were getting this very wrong, so I'm going to look for partial credit on the quiz you took on polar last week. But make sure you can do this, that you can name the 3 points. All right, so this page relates to what has now been changed to be the Desmos activity. But what you might want to do as you do the Desmos activity is fill out some of these curves. Now, there's a lot of them on this page and the next. I'm really only going to talk about 3 on this page, which I think is page 12 or 13. It could be different in your packet because this is, well, actually it should be the same. I was going to say this is last year's packet, but not in my flip chart. So again, when we're talking about these equations, they're always in terms of polar variables like r and theta. So when I look at these 2 equations and I think about them in terms of what I've learned so far in trig, in this school year for math, and last year for honors algebra 2, I have thought of these equations as sinusoidal transformation equations. Okay, so each one of these letters, D moves a graph vertically, A is our amplitude, B helps us determine our period. And all of these equations, when I think of them as sinusoidal transformation equations, are y equals. Now, that's not the same for a polar graph. When I'm doing a polar graph, this is the generic polar graph equation. Our function graphs are y equals. I know this is a polar graph, and I'm doing a polar graph, say, exploration, because the equation is equal to r, the generic polar graph equation. So right now, I'm going to switch to GeoGebra, and I'm going to start with this first equation. Now notice, for this group of equations, these are circles, and the equations are generally in this format. So I'm going to go to GeoGebra, and you can see over in the upper left-hand corner, I have the equation, and it says f of x equals, but you know, we're doing it, as you can see, both polar and Cartesian, xy. So I have f of x equals 2 cosine x, as is on your paper in your packet. And what happens is, at least on the left, I'm looking at this graph as if it was Cartesian, as if it was an xy graph, and I'm graphing a typical cosine curve. Now watch what happens on this xy plane as I move from 0 to 2 pi. Now 2 pi is 3.14 times 2, so the A is our x-axis, the f of A is our y-axis, and that is a typical cosine curve. It's not the parent curve because the amplitude is 2. How do I know? In the equation, 2 is the coefficient. And also when I look at my Cartesian graph, my maximum is 2, my minimum is -2. The midline is still y equals 0 because I'm not adding or subtracting anything to cosine x. We will add or subtract numbers later. Now I'm going to move this over so you can see what happens with the polar graph as I move from 0 to 2 pi. Okay, so remember, it's like trig, 0 to 360, 0 to 2 pi. Our cosine curve in one cycle goes from 0 to 2 pi. So that's why we've chosen those A values. So here is my polar graph. Let's see if I can move this down. There we go. All right, here I go. I'm going to move from 0 to 2 pi again. Watch the graph on the right this time. All right, so you can see on the polar grid, they're starting to graph the equation of a circle. When we were in our packet, we said Those first equations we're looking at are equations of circles. Now, the green circle is not part of the graph. What it's showing you is where I stand in terms of completing the graph from 0 to 2 pi. So let me go back again. The yellow is the curve. The green is where I stand in creating the curve. So here I go. Now watch what happens when I get to 3.14 or approximately 3.14. Okay, I'm going to stop there. The green only shows half a circle. Why? Because I've only gone from 0 to pi. And my circle is complete. My yellow circle is complete. So what happens is, as I go the rest of the way, from pi to 2 pi, and the green circle is complete, saying I have completed one rotation of my polar graph, I've traced over that yellow circle again. That happens a lot with these type graphs. You're going to trace over petals in a rows. You're going to trace over circles because you're going from 0 to 2 pi, just like you did in trig for most things. The other thing I want to point out is what happens in terms of the symmetry. In this graph, it's 2 cosine x. Cosine is mostly associated with x or the x-axis. Notice how my yellow circle is symmetrical over the x-axis. So it makes sense. If cosine goes with our x values, the symmetry of this type of circle polar graph is going to be symmetrical over the x-axis. So now let's try the same thing with a sine curve, and hopefully this will let me change it. Sometimes it does, and sometimes it gives me a hard time. Let's try this sine. Sometimes when I hit tab, it works. Oh, I know. Wait a minute. Hold on. Okay, there we go. So I've got my sine curve. I've got my Cartesian on the left, my polar on the right. I'm going from 0 to 2 pi again. Look where the yellow circle is now. As I draw a sine curve with an amplitude of 2 on the left, my polar graph now forms a circle, but the symmetry is now on the y-axis. Why is it on the y-axis? Because this is a graph of 2 sine x. If it's a graph of 2 sine x, sine goes with y values, symmetry is over the y-axis. And notice I'm not saying even symmetry. This is not a function. Even symmetry means even function. So we don't use the word even. We call this y-axis symmetry. And I just want to do one more equation using GeoGebra. Let me move this back. I'm going to add 1, and let's see what happens. Now, I'm going to tell you right now, this is not going to be a circle. Let's see what this graph looks like. So I'm adding 1. So this is a translation up 1 of the graph to sine x. So the amplitude is still 2, but now it goes from 3 to 1. And as I move the slider from 0 to 2 pi, watch the polar graph. Okay, I'm forming what looks like a circle. Okay, but it's not a circle. Okay, I've gone, let's see, have I gone halfway? No, here's halfway. Halfway, remember the midline changed to y equals 1. So this is approximately the midline. Now, I've got sort of a circle. But as I continue down through the x-axis and complete my rotation of 2 pi, look at your polar graph. Your polar graph has this little loop. This is a limacon. And that inner loop is going to be something that later on in your calculator, I'm going to show you how to measure. And when I say how to measure, what I mean is how to restrict the domain in terms of the degrees to say where that inner loop takes place. And just one other thing that might help you understand where that loop comes from. That loop here near the origin happens where your graph in Cartesian coordinates dips below the x-axis. So watch what I mean. When I move here to the x-axis, look, I've got my green circle saying I'm not finished doing the graph. My yellow circle is pretty much done, but as I dip below the x-axis, you can see the green circle is being complete to say I'm going to finish to 2 pi, and the inner loop is created only for the values that are below the x-axis. All right, so you might want to have taken notes on your packet for that. So we did the graph 2 cosine. We did the graph r equals 2 sine theta. And also down here, again, I told you it was a limacon because it had that little loop. It wasn't exactly a round shape. Notice the transformation or the polar graph equation. Now it's d plus a sine x. We had 1 plus 2 sine x. The d on a Cartesian graph is a transformation up, and the a is the amplitude, and that forms our limacon. And for this one, we did the equation r equals 1 plus 2 sine x, or 2 sine theta. Okay, another kind of curve we're going to talk about. For this, I'm not going to use my calculator or GeoGebra. I'm just going to do this one by hand because I don't think it's as hard. It's actually, I think, a little bit more fun to do this by hand than the other kinds of curves. So this is what these equations look like when, oh, I shouldn't be uncovering this yet. This is what these equations look like when it is a rose curve. A rose curve is any curve created that's got petals. So it looks like a flower. Okay, it may not look like a rose, doesn't look like those kind of petals. It looks more like a daisy. But those patterns are called rose curves. And if you look at the equation, you've got an amplitude, and you've got a change in the period. Okay, the A and the B indicate, at least the B indicates a change in the period. That's different from your circle equation. Your circle equation was just A sine X, A sine X, A cosine X. This one has a number or coefficient in front of the X, and that changes the shape of your polar graph. Now I'm looking at this equation, r equals 2 cosine 3 theta. From our rose patterns or rose curves, the number or the B is going to tell you the number of petals. This one is going to have 3 petals. It actually has 6 petals because you're going to trace over them just like we did with the circle in our first GeoGebra. We got one yellow circle, and then to finish between pi and 2 pi, we traced over that yellow circle again. Well, the same thing happens with these 3 petals. They're actually 6 petals. You get them one time, and then as you finish your complete rotation counterclockwise, you're going to trace over those same petals again. So I also wanted to point out that the amplitude for these kind of curves, the amplitude represents the petal length. So when I look at this graph, first of all, again, it's cosine. Cosine is going to be symmetrical over the x-axis. So if it's got 3 petals that are traced over twice, and it's got symmetry over the x-axis, look at the graph. That first petal goes from 0 to 2. The 2 represents the petal length. And then if I want to complete the symmetry over the x-axis, I'm just going to continue the pattern. 1 petal in quadrant 2, the other petal in quadrant 3. 2, again, the amplitude represents the petal length, and you can see it here, 0 to 2. The symmetry is over the x-axis. 3 petals representing this B value here, and they're traced over twice. I don't think I have anything else on this page. Let me see. No, I didn't do anything else on this page. Okay, on page 15, I'm not going to go over everything. It's lots of A's and B's and D's and a whole bunch of stuff. I just want to show you the 4 types of limacons. Okay, you've got your limacon with the inner loop, which we did, but ours was symmetrical over the y-axis. You've got that cardioid that I was saying before, but again, that's a type of limacon. And then you've got your dimpled limacon, which you really don't need to know, at least not this year, and your convex limacon, which you also don't need to know. Now, this inner loop is very important, just like it was when we did it in GeoGebra. This inner loop for this limacon is determined where the radius is negative. So when I was talking to you about all of the points on GeoGebra, the points, the y values, or in this case, they are the r values that dip below that x-axis, that dip below the polar axis, where the radius is negative, that's where you're going to get an inner loop. And then down here, it's just our rose curves again. Now, a rose curve is unlike the limacons. It's all determined by the B value and the amplitude. But just as a reminder, when n is 3, n is the B value, that number in front of the theta after cosine. If that number is 3, you're going to get 3 petals. 1, 2, 3. They're going to be traced over twice. Now that's not the same when the number in front of theta is even. N equals 3, 3 petals traced over twice. N equals 5, 5 petals traced over twice. This one has got to have sine in it because it's symmetrical over the y-axis. This one has to have cosine in it because it's symmetrical over the x-axis. When the number in front of theta is even, there's not going to be tracing twice. You're just going to take that value, that B value, or in this case n, in front of theta, you're going to multiply it by 2. And in one full rotation, 0 to 2 pi, you're going to get 8 petals. Again, when the number in front of theta is even. Same thing for this last one. N is 2. 2 times 2 is 4 petals. This one has symmetry over the pole. This one has symmetry over the pole. Actually, this one has symmetry over the pole as well. And then we're going to talk about symmetry on the next slide. Okay, so the objective is graph polar equations and determine the maximum R value and the symmetry of the graph. We are going to do maximum R value in Friday's class, and today we're going to talk about symmetry. When I look at the warm-up on this page, it says solve the equation from 0 to 360. Now, I'm not going to teach you how, I am going to teach you. I'm going to show you how to solve it algebraically. You kind of already know how to solve these things algebraically if you know your unit circle, but I'm not really going to require it. I'm going to show you how to do it on your calculator, which I think is actually a little bit more fun to do it on your calculator. So let me talk about the symmetry. Again, it's not symmetry of a function. There is no even symmetry. For number one, when it's symmetrical to the line theta equals pi over 2, here's your unit circle. Here's pi over 2. That's your y-axis. But this is y-axis symmetry. Do not use even. Can't be even if it's not a function. Now, when it says replace theta with pi minus theta, it's only telling you this. It's telling you if in your polar graph you're over here and this point over here is r theta, then this point over here is going to be, it's not going to be negative r, it's going to still be positive r, but it's going to be pi minus theta. Okay, think about when you did Ferris wheels so long ago. This point and this point are the same height. They are symmetrical over the y-axis. Okay, symmetry with respect to the polar axis. Now, polar axis is not the same as the pole. The polar axis is your x-axis. That's something we also learned the first day that we did polar equations and polar coordinates. So it's the x-axis. So now we're going to have x-axis symmetry. Here's the graph. Here is the graph of the equation or the point. If this point is r theta, right here, this down here is going to be r negative theta. Reflection over the x-axis. Last one. If number 2 is symmetry over the polar axis, number 3 is symmetry over the pole. So again, you're thinking of a globe with the North Pole standing up, similar to your origin. Again, you're not going to call this origin symmetry or odd symmetry. No, it's not a function. Don't do it. And for this one, since it's symmetrical over the origin or pole, here is your r theta. And now this one says replace r with negative r. Remember, with negative r, you're going to go in the opposite direction. This is a 180-degree turn to create negative r theta. Or I guess it's, must be pi plus theta. Pi plus theta. Yeah, it's pi plus theta. Sorry. Because you turned 180 degrees. 180 is on the other side of the x-axis. You're adding theta. So it's negative r theta plus pi. Sorry, I'm writing it so sloppy. All right, one more example. I've gone over what I wanted to. I wanted to get about 20 minutes, but I guess that makes sense since Desmos was only supposed to be giving you 20 minutes to do that. And I'm going to talk about example 1, but I am only doing this equation. So if you're looking at this page, I think it's 15. I'm not looking at A. I'm just looking at B. Okay, and we already talked about this graph when we did GeoGebra, but I'm going to show you not only how to determine the type of symmetry, but you guys should already know the symmetry because it's a sine graph. So as soon as it's a sine graph, it's symmetrical over the, okay, it says the y-axis, but of course we're talking polar, so you can't really say it's symmetrical over the y-axis. You really should be saying at this point, symmetrical over the line, theta equals pi over 2, which we already know is basically the top half of the y-axis. So we know the symmetry. It's theta equals pi over 2 symmetry. And now I want to talk about how we would either graph this by hand and also how to figure out how we would restrict the domain to produce the loop. You can see I highlighted the loop in green. How did I get this graph? Well, I took my equation and I substituted in different values of theta as I moved from 0 to 2 pi. So when I'm at 0, I plug that in for theta. My r equals 1. Sine of 0 is 0. 0 times 2 is 0. 1 plus 0 is 1. When I put 90 in, sine of 90 is 1. 1 times 2 is 2. 2 plus 1 is 3. And I keep going. And you can see that I'm getting not a repeated pattern like I normally expect when I have sine and cosine. Notice that when I plug 270 in, I get a negative r value. Notice on my polar graph, there's really nothing here. Well, why is that if I'm here at 270? Because it's negative r. Negative r takes you in the opposite direction. So this green loop that I drew, this little inner loop, comes from the negative r value that I get. Go towards 270, but then because it's a negative r, turn around and go towards pi over 2. So I'm just graphing these points. The polar graph is what you see. So let's talk about the restrictions that produce that little inner loop. And I'm reminding you that this is what the equation looked like in normal Cartesian coordinates. Between these yellow dots I have on this XY graph, that's where you have your inner loop. So if you were doing this on a calculator, you could, I guess, do a line y equals 0. You could not put your calculator in polar mode, and you could just put that equation in y equals 1 plus 2 sine x, and you could find the intersections, and then you could figure out what the restrictions are that create that inner loop. Between, and when I say restrictions, I mean between what theta values, between what angle measurements in degrees forms that loop. So now I'm going to show you how to do it graphically, and then I'm just pointing out, again, I told you, you don't have to do this algebraically, but you can solve algebraically. If you wanted to solve these problems algebraically, how do you restrict the domain? You're going to set your equation equal to 0 because look, that red dot on my graph right here is at the origin. So I want to know how I started at the origin and I ended at the origin. Okay, at the pole. Well, that's where r equals 0. R equals 0 there. So if I'm solving, I set my equation equal to 0. R equals 1 plus 2 sine theta. I get sine theta equals -1/2. And as I know from trigonometry, because this is tying everything together, that's in the third and fourth quadrant. It's where theta equals 210 and where theta equals 330 in the fourth quadrant. So my inner loop restriction using algebra would be between 210 and 330 is where you form the inner loop. But now I'm going to show you how to do it in your calculator. Step 1, change your mode to polar and make sure it's also in degrees. So go down, change it from radian to degrees if it isn't already, and then your calculator is almost always on function. Put it on polar, not function, not parametric, polar. And now when you go to y equals, it's no longer y equals, it's not a function, it's r equals. It knows it's polar. And when I typed in the equation and I hit the x, t, theta, n button, the calculator knows it's in polar mode too because it didn't put sine x, it put sine theta. Now, to make sure that I can see the graph clearly, I'm going to do two other things before I plot this and then determine what the restrictions are on the inner loop. One is I'm going to change my window. Okay, so now notice it's not just x and y. If you were using parametric form in your calculator, which we didn't really cover very much, you would have seen t, x, and y. But we've got theta, x, and y. So since your calculator's in degrees, you're going to go from 0 to 360. Notice my theta step. That means in what kind of increments do you want me to draw the graph? I want you to make those increments very small. Mine is 0.1. Why? Because I want to see how the graph unfolds as it moves from 0 to 360 degrees. If I put anything like 0.5 or even 1 degree, it's going to form that limacon so quickly you're not really going to see how the graph was formed. So make that small. In terms of my x minimum, I kind of looked at my table and said, well, I'm going as low as -1 and I'm going as high as 3. So I just made sure that my x max and min kind of covered that. And then in terms of my x scaling, I made sure that I did it by, it looks like half a pi. Looks like half a pi. Actually, it looks like okay, I have to think about that a second. Why am I counting by half a pi? All right, well, I mean, I'm looking at my thetas. I'm looking at my r values. They're not very large. Everything's going to be near the pole. So I'm sort of making sure that it unfolds slowly by my small steps, 0 to 360. And then in terms of where I see the top and the bottom and the left and the right, it's all within a range of, 4 to 8 units. The other thing I want to do is something that many of you may not be familiar with, and that's your format button. You want to hit second, format, and I don't remember what GC stands for, but you do not want it on rectangular GC. You want it on polar GC, and that's going to become important when you use your trace button for where the inner loop is. So now I think I'm finally ready to graph. My equation is in, my window is set, my format is set. I'm going to hit the graph button. Watch how slowly the polar graph unfolds. See, it doesn't look like a polar graph, but again, when I'm setting the x and y axis, I'm just making sure I can see. Now, that limacon unfolded very slowly. which is great because notice how that inner loop was formed before the graph completed 360 degrees. So the inner loop happens before I get to 360 degrees. And now, just like solving algebraically, I want to figure out, using my trace button, what the limits or what the restrictions are for theta to form that inner loop. You're going to hit the trace button. Now, if I try to go to the left using this arrow here, notice how I can't get anywhere. That loop was formed almost at the end of the graph. So I can't get to the loop by going to the left. Besides, it says my theta is 0. So if my theta is 0, I'm already at the beginning of this limacon. Use your right button. Keep going until you get to r equals 0. That's just like when you did it algebraically. I don't know why it's not moving. Why is it moving? Oh, the problem it's moving so slowly is because I have it moving at 0.1 increments. Okay, this is going to take a really long time. All right, so sorry. I can't seem to get it to move faster. There we go. Yeah, see, advantage and disadvantages to making your scaling, to making your scaling 0.1. When I had it at 0.5, here, let me change it to 0.5 because now you've seen the graph unfold, but now it's taking too long to get to window. Now it's taking too long to get to the inner loop. So 0.5 graph. Actually, it didn't actually unfold that that quickly. Trace, move to the right to get to the inner loop. You can see it's moving a bit faster now. Okay, I want to go where r equals 0. I'm getting close to the pole. I'm almost there. Boom, r equals 0. Look, theta is 210 degrees. That's the beginning of my restriction of the domain. Now, as I continue to move to the right, it's going to go around the inner loop only. And I'm going to keep moving right until I get back to r equals 0. If it's like algebra, the algebraic solving, it should be 330 degrees. Boom. R equals 0, theta equals 330. So that's how you would do it with your calculator. Okay, I'm sorry this lesson was so long. I hoped it helped. I will see you on Friday, and for those who had trouble with this lesson, I hope to see you Friday for extra help at 8 a.m. Good night.